species, we have always been fascinated by the stars. When twilight deepens and thousands of pinpoints of light appear in the night sky, we are naturally moved by the wonder of it all, and by our desire to understand it. But for all those who ponder the nature of the stars, the universe poses a special challenge, because how can we hope to understand what we cannot touch?
The remoteness of the stars means that we can't just reach out and grab them to see what they're made of. But remoteness is not an insurmountable barrier to understanding. Over the centuries, astronomers have learned that the stars do reveal their secrets when we learn to look at them in the right way.
At first, ancient thinkers compared the stars to what they knew from everyday life. Around 450 BC, the Greek philosopher Anaxagoras reasoned that the stars must be like stones glowing with extreme heat, but too far away for us to feel their warmth. In fact, there was an element of truth to this. But when Aristotle looked to the stars a century later, he disagreed. Aristotle said the stars couldn't be made of fire, stone, or anything that we experience on Earth, because stars behave differently. Instead of moving in straight lines, like falling objects, the stars spin in circles around us as they rise and set each night. And the stars never seem to change. Aristotle thought they were eternal, made out of a heavenly substance called the ether. Aristotle's ideas would hold sway for the next 18 centuries, until astronomers started to see things differently. First, they realized that the stars aren't spinning in circles after all. It's we who are spinning, by living on a rotating planet that is also following a curving path around the sun. Then, in 1572, a brilliant new star suddenly appeared in the constellation Cassiopeia. For a time, it outshone every other star in the sky. After many months, it gradually faded from sight. Today, we know this celestial interloper was a supernova, the explosive death of a massive star. The remains of that explosion can still be seen as a vast bubble in space, over 8,000 light-years away. But what really mattered to astronomers back then was that the supernova proved that even stars can sometimes change. Then came the telescope, the device that revolutionized astronomy by making distant objects appear closer. Through the telescope, the planets were transformed from dots in the sky into full-fledged worlds. The telescope also confirmed that the stars were much further away than ancient astronomers had ever imagined. Far enough to be distant versions of our own sun. Increasingly, it no longer made sense to think of heaven and earth as separate. Both are governed by the same principles. In 1687, Isaac Newton demonstrated this once and for all by showing that his famous law of gravity applies to the moon and planets just as it does to apples falling from a tree. But it was another discovery of Newton's that would ultimately allow astronomers to learn what stars are made of. In his book on optics, published in 1704, Newton showed how white light is a combination of all the colors. With the help of a prism of glass, those colors can be separated into a spectrum, like a rainbow. Newton explained how rainbows work, but it wasn't until 1802 that an English chemist named William Wollaston took the spectrum one step further. Wollaston improved the separation of the colors of light by first passing sunlight through a narrow slit and then a prism. That's when he noticed that the sun's spectrum contained a few thin, dark lines. Wollaston thought the lines were borders separating the colors, but he had only seen the tip of the iceberg. In 1814, a German instrument maker named Josef Fraunhofer invented a device for measuring the refraction of light through different types of glass. When used with sunlight, the device allowed Fraunhofer to see the same dark lines in the spectrum that Wollaston had seen. But he also saw hundreds more. Fraunhofer didn't know it yet, but his device, called the spectroscope, would eventually be used to crack the mystery of what the sun and the stars are made of. But not until someone could figure out how to read the hidden message in those lines and turn a celestial barcode into a new form of astronomical knowledge. In the scientific journey, there have always been moments when progress has seemed impossible. That was the case in 1835, when the French philosopher Auguste Comte wrote that the chemical composition of the stars would forever be beyond the limits of human knowledge. Comte assumed that scientists would have to travel to the stars to learn what they're made of. But thanks to the invention of the spectroscope, he was soon to be proven wrong. The spectroscope works by dispersing light into a spectrum of colors, from red to violet. It also shows that the sun's spectrum is riddled with fine dark lines. Because light is a wave, the lines mark particular wavelengths where some of the energy in the sun's light has gone missing. But where did it go? In the 1850s, two German physicists, Robert Bunsen and Gustav Kirchhoff, teamed up to find out. Their experiments showed that when light passes through a gas, the atoms in the gas absorb some of the light, but only at certain specific wavelengths, which depend on the properties of that particular type of atom. That explains the lines in the sun's spectrum, which are called absorption lines. Kirchhoff and Bunsen realized the lines act as a chemical fingerprint because they reveal which gases are present in the sun's atmosphere. But that's only half the story. When atoms are energized in the right way, they can emit light too. This creates a spectrum of bright lines, known as emission lines, which are the counterparts to the dark absorption lines.
For astronomers, all of these spectral lines, both bright and dark, revealed a link between the Earth and sky. In the laboratory, they could measure the spectra of gases and flames using known materials. Then they could compare these results to the spectra of the sun and stars. For the first time, the chemistry of the universe was on display.
Starting in 1862, the English astronomer William Huggins was among the first to attach a spectroscope to his telescope and explore the heavens in a new way. He was later joined by his wife and scientific collaborator, Margaret. From their home-built observatory near London, Huggins recorded the spectra of many stars and other celestial objects. Among his targets was the Great Nebula in Orion, a misty patch of light located near the stars of Orion's belt. Huggins found that the nebula's spectrum consisted entirely of bright emission lines, especially lines corresponding to hydrogen. Here was evidence that the nebula was really a vast cloud of glowing gas, perhaps a cloud that might someday condense to form new stars. In 1864, Huggins saw something a bit different when he turned his spectroscope on the Cat's Eye Nebula, an expanding shell of gas blown off of a dying star. The Cat's Eye produced a bright green emission line that didn't seem to correspond to any known element. Huggins dubbed the mystery substance nebulium. It would take over 60 years before astronomers realized that the green line is produced by atoms of oxygen with 2 electrons stripped away. This energized state reveals the high temperature and low pressure environment within the nebula, which is expanding at nearly 60,000 kilometers per hour. In 1868, the spectroscope really did lead to the discovery of something entirely new. In August of that year, French astronomer Jules Janssen used a spectroscope during a total eclipse of the sun. Janssen was hoping to isolate the light from a solar prominence, a glowing ribbon of ionized gas suspended in the sun's powerful magnetic field. Normally, prominences are impossible to see because the surface of the sun is so bright. But during a total eclipse, any large prominences on the edge of the sun are immediately visible to the eye. And when Janssen turned his spectroscope on one of them, he saw some emission lines he didn't recognize. In fact, they didn't correspond to any known gas. Janssen soon found he could spot the same emission lines in the sun's spectrum without needing an eclipse to do it. At the same time, in England, an astronomer named Norman Lockyer had seen the emission lines too. Like Janssen, Lockyer recognized that the lines were produced by a previously unknown element. He named it helium, after Helios, the Greek god of the sun. It would take 27 more years before the existence of helium was finally confirmed in the laboratory, but its discovery on the Sun made Jensen and Lockyer famous. Lockyer went on to become the founding editor of the scientific journal Nature. By the end of the 19th century, the spectroscope had proved its worth in decoding the chemistry of the Sun and the stars. But its greatest triumph was still to come. By 1925, it seemed that the quest to understand what stars are made of had come full circle. 24 centuries earlier, Anaxagoras had written that stars are fiery stones. Now the spectroscope was suggesting something similar. By pointing it at the Sun and at distant stars, astronomers could see spectral lines that corresponded to sodium, calcium, magnesium, iron, and many other elements that are commonly found in minerals on Earth. This persuaded the American astronomer Henry Norris Russell to suggest that if Earth's crust were heated up to the Sun's temperature, it would share the Sun's spectrum. Russell was a leading authority on stars, and his view defined the scientific mainstream. But Russell's universe was about to change. The groundwork for that change had been laid years earlier by a remarkable group of women in Cambridge, Massachusetts, who were hired to work at the Harvard College Observatory. In an age before computers, the observatory's director, E. Pickering, was dealing with a vast flood of new data from the heavens. The development of photography and spectroscopy together meant that the spectra of thousands upon thousands of stars could now be captured and recorded on photographic plates. It was a data overload, and Pickering needed help. He didn't have the budget to hire an army of astronomers. So in 1881, Pickering hired his housekeeper, Wilhelmina Fleming. Fleming had been a school teacher in Scotland, and she soon mastered the art of cataloging stars according to their spectral lines. She came up with her own classification scheme and ultimately examined some 10,000 individual stars on photographic plates. Pickering hired more women to help and put Fleming in charge. Over the next 30 years, they would lay the foundations for modern astrophysics. One of the most important members of the team was Annie Jump Cannon, who arrived at the observatory in 1896. As she gained experience, Cannon became truly prolific at cataloging stars based on their spectra. At her best, she could catalog 3 stars per minute. It's estimated that over her lifetime, she classified about 500,000 stars by eye, more than anyone else in history. As she worked, Cannon hit upon a more advanced system for classifying the stars. Her approach showed that there was a progression in the spectral lines as one moved from star type to star type, with some lines becoming stronger and others fading away. This was an important clue, but it would take another astronomer to understand what it meant. Cecilia Payne grew up in England, where she became fascinated with the science of the stars. But she soon learned that opportunities for women in astronomy were virtually non-existent. In 1923, Payne arrived at Harvard College Observatory to join a newly launched graduate program there. Working with Cannon's data, Payne began to see the underlying physics behind the classification scheme. She realized that a spectrum is really a way to measure a star's temperature. Stars at different temperatures energize the atoms of various elements in different ways, leading to a unique set of spectral lines. But Payne's analysis also showed something else. The dominant element in all of the stars appeared to be hydrogen. In 1925, Payne summarized her findings in her PhD thesis. But when Henry Norris Russell read an advanced copy, he thought her conclusion about hydrogen had to be wrong. Payne then added a line to the thesis that undermined her boldest discovery. Within 4 years, Russell realized it was he who was wrong, and he admitted it.
Cecilia Payne's astonishing insight was correct. Today, astronomers know that hydrogen is the most abundant element in the stars, and that points the way to an amazing scientific story.
It's now clear that stars are born out of clouds of hydrogen gas, like the Orion Nebula that William Huggins once studied. Once they form, the stars shine because of nuclear reactions that turn the hydrogen into helium and other heavier elements. Eventually, stars die, and the elements they've created are released back into space, just as they are in the Cat's Eye Nebula. In the process, the stars are seeding the universe with the raw material needed to produce planets and life. This is the great secret that the spectroscope has revealed. A secret unraveled over a century and a half by a succession of remarkable men and women. Thanks to them, we now know what stars are made of. But in a very real sense, we've also learned that we are made of stars.